Hi, so in this video I'm going to show you how to derive and then apply the Maclaurin series. And what the Maclaurin series does is it allows us to represent any function as a power series. So if we have this function of x here, I'm going to show you how we can go from this function to this expansion, and it is this which is the Maclaurin series. So the first thing we're going to do is we're going to work out f of 0. So this means we're going to let x equal 0. And then if we substitute f of 0 into here, then we get a0 plus a1 times 0, so that becomes 0. For a2, well, 0 squared is 0, so again that becomes 0. And in fact, all of these terms will cancel to make 0. So what we're left with, to work out a0, this is simply the function when x is 0. So now we're going to work out a1. And the way we do this is, if we work out the first derivative, so f dash of x, well, this constant will go, because it's just a constant, and this x will go, so we're left with a1. And when we differentiate a2 x squared, this 2 will come down, so we'll get 2 a2, and then the x will lose 1 from that power. So for our next one, the 3 will be multiplied by a3, so we get 3 a3, and then lose 1 from that power, so it becomes x squared. Then we get 4 a4, and again we lose 1 from the power, so x cubed. And then 5 a5, or 5 lots of a5, and that's x to the 4, and that would carry on. So now again, if we substitute in x equals 0, well, here we'll have a1, because again this is just a constant. If we substitute in 0 here, all of that would become 0, as it will here, and so on. So therefore, we know that a1 is equal to the first derivative when x is 0. To work out a2, we need to cancel out this x term, which we can do by finding the second derivative. So the second derivative of x, well, this constant will go, and this x will go. So we've got 2 lots of a2. This 2 will come down, so we've got 3 times 2. And then we'll lose 1 from this power, so a3, and then x. For a4, this 4 here should actually be here. So you've got the 4 times the 3, a4, and lose 1 from that power. So for the next one, we've got 5 times the 4, a5, and then x cubed. And again, to work out a2, we'll substitute in x equals 0. So you've got 2a2, and the rest of the terms will cancel to make 0. So now we can say a2 will be the second derivative of 0 divided by 2. So now we'll work out a3. And to get rid of the x again, we'll find the next derivative. So we've got the third derivative of x. This constant will go, as will this x. So we've got 3 lots of 2, a3. This 2 will come down, so we've got 4 lots of 3, lots of 2, and then we'll lose 1 from this power, so a4, and then x. This 3 will come down. So we've got 5 lots of 4, lots of 3, a5, x squared. And that will carry on. We'll substitute in x equals 0. So we're left with 3 lots of 2, a3, and the rest of these will cancel to make 0. So a3 will be third derivative of 0 divided by 3 lots of 2. Okay, so at this point we should see a pattern. Can you see that the next set of solutions will be the fourth derivative of 0, and this will be 4 lots of 3, lots of 2, and then a4. So this will give us a4, the fourth derivative, 0 divided by 4 times 3 times 2. And actually what we could have done here, we could also put a 1 here. So I'll do that and you'll see why in a second. So we'll divide this by 1, we'll divide this by 1, and 1 as well. And actually we can do the same here. So now you should recognize these as a factorial function. So if we go back to f of x, we have AO, which is FO. So f of x will be AO FO plus A1, which is this one here. So f dash of O. And then you've got your x term here, plus A2, which is this one here. So the second derivative of 0, x squared, over 2 times 1, which is 2 factorial. Then we've got A3, which is this one here. And this is the third derivative of x cubed over 3 factorial. And then A4, the fourth derivative of x to the 4 over 4 factorial. And this series would go on. So we're left with the rth derivative of 0 over r factorial multiplied by x to the power of r. So this is the Maclaurin series. Okay? So I hope that gives you an idea of where this comes from. What we're going to do in example 2 is apply this series to write a function as a power series. Okay? Let's move on to question 2. Okay, so in example 2, we've been asked to write the Maclaurin series of the function e to the 1/3 x in ascending powers of x up to x to the power of 4. And then for part B, we're going to use this series to approximate the cube root of e squared. Okay? So the first thing we need to do is we need to find the higher level derivatives. So we'll write these in terms of x. So we're told that fx is equal to e to the 1/3 of x. So the first derivative, while using the chain rule, we'll differentiate the inner function and we'll bring that down. So that'll become 1/3 of e to the 1/3 x. The next derivative, we'll do exactly the same again. We'll differentiate 1/3 x, we'll bring that down. So this becomes 1/9 of e to the 1/3 x. The third derivative, again we'll bring the 1/3 down, so that becomes 1/27 of e to the 1/3 x. And then the fourth derivative will become 1/81 e to the 1/3 x. So now we need to let x equal 0 for each of these functions. So f of 0, in this case, well, 1/3 of 0 will be 0, and e to the 0 is 1. For our first derivative, again this is 0, so this is 1, so this will become 1/3. And actually, each of these will become 1, so each of these will become our solutions. So the first derivative of 0 will be 1/3. The second derivative will be 1/9. The third derivative, 1/27. And the fourth derivative, 1/81. So now we can substitute each of these into our expansion. So f of x will be f of 0, which we have as 1, plus f dash of 0 x, which is 1/3 x, the second derivative of 0, which is this one, x squared over 2 factorial. So we'll say 1/9 of x squared over 2 factorial. The next one will be 1/27 x cubed over 3 factorial. And then we'll get 1/81 x to the 4 over 4 factorial. We can simplify each of these on our calculators. So fx will be approximately, I should change this to approximately, because we're only looking up to a fourth term, will be 1 plus x over 3 plus 1/9 divided by 2 will be x squared over 18. This one I'll do on my calculator. So we have 1/27 divided by 3 factorial, which gives us x cubed over 162. For our next one, 1/81 divided by 4 factorial, which gives us x to the 4 over 1944. Okay, so that's part A. For part B, we've been asked to approximate the cube root of e squared. But we can write this as a fraction, and this will be e to the 2/3. And we can separate this out using the power rule of indices. And this will be 2 lots of 1/3. So if we compare this to our function of e to the 1/3 x, we can see that this x is actually 2. So x is equal to 2. Now all we need to do is substitute this 2 into our approximate expansion. So the cube root of e squared will be approximately 1 plus x over 3, so 2/3, plus x squared, so 4 over 18, x cubed, so 8 over 162, and x to the 4, which is 16, over 1944. And we can work this out on our calculator, and we get 473 over 243, which is approximately 1.9466 to 4 decimal places. And we can compare this to the actual solution. So we've got the cube root of e to the power of 2. And the actual solution comes out as 1.9477. So you can see that this would have been more accurate if we had gone to more powers of x. Okay? Well, thank you very much for watching. I hope you found that useful. You can download the full lesson and worksheet on my website, mrmathematics.com. Thanks again and take care.